Hello, OWASP Ottawa, and welcome to our July meetup 2022. Hope you're having a great summer day, afternoon, evening, or whatever time and space you're watching this in. Um, we're very, very pleased to have a serial presenter, alumni presenter to OWASP Ottawa to talk about and provide an introduction to reverse engineering. It's a subject that I want to learn more about, and this would be a great presentation to watch and rewatch and rerun many times to be able to learn this important subject. This evening, we have Dmitriy, who is a senior security researcher at Vectra AI, and where he works on threat detection in the cloud and on-premise networks. Before that, he was a penetration tester at IBM, and after having an extensive experience in software development on many different types of software and systems, if that wasn't enough for you, he has a PhD in computer science. He has a rap list of certifications, including OSCP, CISSP, CSP, and CEH. So I'm sure that Dmitry has an extra brain in a jar next to him on his desk. So without further ado, welcome, Dmitry.
Yeah. Thanks a lot, Gareth, for an awesome introduction. All right. Hello, everyone. Great to be back. I long for the time when we can do this in person. Hopefully, not in too distant future.
So, actually, while we're actually talking about that, that is something that we want to do. The challenges is venue because our original venue no longer exists. So, finding a different venue with all the mod cons of a screen and a projector and places to sit is an issue. But I'm sure we can find something as we are entering the seventh wave, seventh, eighth, 20th. Anyways, whatever wave we're in at the moment, when we sort of feel it's safe and have a venue that is safe for everyone, we will definitely be doing that. But that's something that is a continual discussion. So based on previous surveys, the venue has to be downtown. Everybody wants it to be downtown because it's central to all areas of the city. So stay tuned. When we have something more together, with a safe area, so we're not generating a technical penetration testing super spreader event, then we will definitely do that. But I will look forward to that day as well. Sorry, I prattled.
Great. Okay. All right. So, can you guys see my slides?
Definitely, we can see it.
That's perfect. All right. Okay. So, the title of the talk is "All Software is Open Source." And it's basically an introduction to reverse engineering. Garth already spoke about who I am. Here are some handles on social media if you want to get in touch. As you might have guessed, reverse engineering is my favorite area in security. It's just something that's really, really enjoyable. That's what I try to do as much as I can when I have time. And the reason that I did this, prepared this talk, is that while I have been in security for a few years now, whenever a topic of reverse engineering comes up, I notice that there are a lot of people that find it kind of mysterious. They're hesitant to even touch it. And I always felt that it's something that a lot more people should enjoy, should get involved in. And I've really found it very, very useful in my work in security. So this is my attempt to hopefully makes reverse engineering a little more approachable if you have never touched it and are curious about what it is all about. So here's a quick agenda. We'll just start with a general description of what reverse engineering is and what its applications are. We'll talk about what you can reverse and, in general, why do it in the first place. I'll mention some legal issues that may arise when you engage in reverse engineering, and then we'll talk about different categories of reverse engineering. I'll show you some code examples and tools, and we'll talk about some common obstacles to getting into the field and kind of proceeding with solving challenges. I will outline a plan that I think is a good blueprint for how you can start getting into the field and how you can practice. I'll talk about just general strategies, and then we'll wrap up with the resources. So what is reverse engineering? So this is kind of the, I guess, the encyclopedia definition. It's a process of understanding how a device, system, or a piece of software works by examining it. And the key part here is that you do not have access to the original design specs of this system. You do not have the source code. You don't know how it really is built, what its architecture is, and you're just, through external examination and through taking it apart, you're trying to figure out how it works. Reverse engineering becomes necessary when original design information for, let's say, a system or a process that you're trying to study is either not available or is intentionally withheld. And if you think about it, reverse engineering has been done by humans forever, since the beginning of time. Let's take one invention. Let's say invention of the wheel, for example. Let's say one particular tribe comes up with the design of the wheel, and all of a sudden they start making these carts that can help them, move heavy objects from place to place. So they have this wonderful invention, but they may be hesitant to share it with other tribes in the area. And the only way that knowledge is going to spread is by other people just literally observing them using this invention and then trying to replicate it. So that's essentially reverse engineering. You're observing something, you try to figure out how it works, and then you try to maybe make a working copy of that. And if you think of all kinds of inventions throughout history, in many cases, that's how knowledge about these new things have spread, because I'm sure people weren't always, eager to share something new that they have come up with. All natural sciences, if you think about it, are essentially reverse engineering. Nature doesn't come with a blueprint or a manual, so we have to, through the process of observation, to discover how everything around us is built or created. You basically, science is a process of observation and documentation done in perpetuity. So you try to figure out how things are put together, you document it, and you just do it on, and you share that documented knowledge with other scientists. So that's essentially how all scientific process is working. It's all reverse engineering. And even if you have never done reverse engineering of software, for example, you've probably done it in other areas of your life. When you were a child, you probably tried pulling toys apart to see what's inside. If you have some appliances in your home, let's say something broke, you want to fix it, you'll probably disassembled a clock or two, or stereo, trying to fix something, not always successfully. But when you're doing that, you're essentially doing reverse engineering. You're trying to see how things are built and maybe figure out what to do next, maybe fix something, maybe improve something. There are a lot of modern uses for reverse engineering. first and foremost, there's security and vulnerability research, but there's more. I used to be a pen tester, and reverse engineering is actually very useful skill when you're doing penetration testing, because even if you're doing penetration testing for a client that's very forthcoming with, let's say, design specs, they may not always provide source code. So you may end up having to pull the software you're examining apart and trying to understand what the code actually looks like in order to find vulnerabilities. Malware analysis is a very obvious example of reverse engineering. Malware does not come with any kind of description. It's a black box, and it's your job as a malware analyst to pull it apart and understand what's inside. Military and intelligence work, there's a lot of reverse engineering in there. Nations are always kind of observing other nations, whether they're friendly nations or their adversaries. They try to figure out how, let's say, new pieces of military equipment are built by, say, their adversaries. They try to figure out how to maybe replicate those technical achievements. So it's a very important skill in that area of knowledge. Scientific research, I already mentioned. There's a lot of reverse engineering essentially in there. There's some commercial research and product compatibility research that's pretty much reverse engineering. One example that comes to mind is that if you take printer cartridges, you may notice that you can buy printer cartridges for laser printers or jet printers that are built by the original equipment manufacturer, let's say Hewlett Packard or Canon, but you can also buy models that are built by some other companies. And I suspect that those companies do not always get permission, and probably very rarely get permission from the manufacturer of the printer to build a compatible product or get the blueprints or knowledge how to do it. And I suspect that they take the cartridges that are shipped with the printer, they reverse engineer them, they understand how they work, and then they replicate. There's also area of independent quality control. There are all kinds of consumer consumer agencies such as Consumer Reports, for example, that would buy products to compare and report on their reliability, and they often pull things apart and examine how, let's say, different models of washing machines are built. So there's some reverse engineering in there. Ottawa is an interesting city. Is that I noticed that there are several companies in Ottawa where that deal specifically in examining microchips for patent infringement. So they take a chip, they look at the microcode embedded in the chip. They look at firmware, they look at how chips are put together, and they try to spot maybe certain designs that were invented by one company that holds patents for them, and then they replicate those design, and then another company chooses to replicate those designs in their own product. So it's an interesting field where you examine a product and try to fully understand how it works, and then spot if there's any patent infringement. So and there are many other uses for reverse engineering, and that's not necessarily software. We will talk about software reverse engineering in this presentation, but these days that includes most of hardware too, because most of modern hardware is driven by software. So why should you do reverse engineering? So a lot of software and hardware around us are essentially black boxes. The documentation is scarce or not available. Architectural blueprints are almost never available, but at the same time, we may want to analyze the particular product for its safety or quality. Maybe if we're a security researcher, we want to look for security or for security vulnerabilities or maybe hidden backdoors. If you're dealing with a legacy product for which a manufacturer may no longer be around anymore, you may want to recover legacy knowledge in order to build something compatible. So let's say you have a type of furnace on the market that's really old, manufacturer no longer makes them, blueprints are not available, but you need a particular replacement part for that. So the company that builds replacement parts may pull that furnace apart, figure out how different parts are put together, and build replicas. So that's a useful application of reverse engineering. I already mentioned printer cartridges, so building compatible products is an important area. And also, if you have something, sometimes you want to change how it works. You may want to modify it. You may want to fix a particular problem that manufacturer is unwilling to do. So for all of those cases, it's very useful to have that kind of skill set where you can open things up and look inside and figure out how things work. And reverse engineering gives you that power. And there's this quote that I really like. I don't know who the author is. If you do know, let me know. When you know assembly, meaning assembly language, all software is open source, and that's I would say that's very true. Once you have that skill, there's really no software out there that's a black box anymore. You can open up pretty much anything and study it. Why should you specifically do reverse engineering? I would say if you're in information security, it's more and more becoming an essential skill. If you look at vulnerability analysis for most CVEs that are published out there, most of them require some part of reverse engineering knowledge in order to figure out how a particular vulnerability can be triggered, for example. So it's a useful skill for that. I already mentioned pen testing. It really helped me in my job as a pen tester when I was able to look at the source code, even when the customer maybe was unwilling to provide the source code. It really helped us find more and more vulnerabilities when we no longer treated a piece of software as just a black box. Incident response often requires reverse engineering because you have to deal with samples of ransomware, malware. There are phishing emails that are encoded in all kinds of interesting ways. There are command and control frameworks that you have to deal with. There are remote shells that are dropped that you want to analyze and see how they work and how you can stop them. So it's really important for security. But reverse engineering really can be lots of fun too. It really gives you the sense of discovery, accomplishment. You're solving challenges. You're overcoming obstacles. You're discovering secrets. It's really exciting, and you will like it probably if you like putting together puzzles, if you like to solve crosswords, if you like to do geocaching and do similar activities. It's really a very interesting intellectual pursuit and really a great exploration activity. So what can you reverse? You can reverse pretty much anything. Of course, Windows, Mac OS, Linux, natively compiled executables. There are executables that are compiled in a portable way, such as Java applications, .NET applications, Python applications. There are all kinds of mobile applications that can be reversed. Minified, obfuscated JavaScript and WebAssembly. There's obfuscated PowerShell, Visual Basic applications for Office. Automation scripts are often compiled, and you may want to figure out how they work. There's BIOS and bootloaders, shellcode, hardware, firmware. It's just the list is endless. Pretty much anything that's software you can reverse engineer. So now it's important to touch on legality of doing this before we actually jump into reverse engineering, because you want to be safe first and foremost. And huge caveat: not a lawyer. Don't even play one on TV. This is not legal advice. I I'm complete amateur in this field. So this the information I'm going to present in the next few slides is something that I could gather just by reading things on the internet. So take it with like a bucket of salt, not a grain of salt. So is reverse engineering legal? Well, as with many complex things in life, the answer is it depends. And you may notice that most license agreements actually prohibit reverse engineering. So if you look at Apple iOS license agreement, Windows license, and many others, they specifically say we don't want you to reverse engineer our products. Period. And it kind of makes sense. Vendors want to protect their intellectual property, and also I think there is also a hidden desire not to not to have flaws be easily discoverable. So you'll very often find these license clauses. And there are existing laws that do restrict reverse engineering. So there's DMCA, Computer Fraud and Abuse Act, copyright law. There are certain EU directives, and there are many others. So you have to be aware that law in general frowns on reverse engineering. You do have more protection if you engage in reverse engineering if you do own the device or a piece of software that you're reversing. I've seen this mentioned many times. So if you, let's say, if you bought a washing machine and you're pulling it apart, you have more protection than if you just went to your friend's house and doing it there. Same thing for software. If you bought a piece of software, you have more rights to look at what's inside. So that's one thing to keep in mind. There's something called fair use defense in copyright law, and it says that you could use copyrighted work if you could use copyrighted works for good faith security research, and it's fair use. So if you are doing reverse engineering as part of security research, you're probably also more or less in the clear. Under Digital Millennium Copyright Act, legal owner of the program may reverse engineer it and circumvent its protection to achieve interoperability. So that's yet another case where, but let's say you have a particular piece of software and you're developing another component that you want to plug into that software, but you don't have documentation. You could legally reverse engineer that to achieve that interoperability. And in general, intent and what you do with information discovered through reverse engineering is key, and we'll talk about that in the next slide. As I mentioned, I'm not a lawyer, but there are lawyers out there that wrote about various topics in security and including reverse engineering. So this is an interesting document that you could look at. It describes different security related activities and their legality. I would recommend that if you're curious to know more, that's one good document to look at. So in my mind, there are kind of three different categories of reverse engineering, and uh, I arrange them from safe to being very dangerous. So if you look at non-commercial software, like maybe open source software that was compiled, or of course anything that you yourself produce, you're in the clear. You can pull that apart, and there shouldn't be any problem with that. And also, I would argue that even if you look at commercial software, but you do it in the privacy of your own home, you do not publish the results. You just do it for learning, for practice, trying to understand how things work on the inside. But you don't take advantage of that knowledge publicly. I think also nobody will probably come after you. You're not really hurting anyone. And then, of course, malware analysis. I mean, it's fair game. Malware authors, even though they may be upset, they won't be able to do anything about you reverse engineering malware. But the next category is where I would be more careful. Reverse engineering of commercial products for security research, even though it's mostly legal, there could be some edge cases where companies may actually become upset that you try to decompile their software. So, and I think there are examples in history where that happens. So you have to tread more carefully there. If you do it through a bounty program, there are some additional protections there, but you have to read the license agreement and the rules carefully. You could probably publish limited reversed code and data as part of responsible vulnerability disclosure. You can actually see a lot of researchers doing that. When a major vulnerability is announced, they would publish really tiny snippets of decompiled or disassembled code that shows exactly the problem where the vulnerability is in the code, but they do it in a very limited, controlled fashion just to illustrate the problem, not to disclose large chunks of proprietary software. And also, if you publish tools based on uh, things you discovered through reverse engineering, also it's kind of it depends on reaction of the company that for which you reversed the software. There were actually famous legal cases concerning reverse engineering. There was a case of circumventing DVD copy protection, and the person in question was acquitted. There was a person arrested in 2001 for circumventing Adobe protection, again through reverse engineering, and charges were dropped. But you really don't want to be in that kind of situation, even if in the end things work out fine for you. You don't want to be in legal hot water. And just know that even if what you're doing is not breaking the law, companies can still come after you and harass you. They have deeper pockets than you do. So you have to be really careful when you're going public with results of your reverse engineering efforts. But I think as long as you do things privately and do it for learning, for training, for acquiring that skill, I think you're in the clear. Finally, there are cases where you're treading on really dangerous ground, and that's usually when what you do endangers companies' profits. They tend to react very nervously to that. So large-scale disclosure of proprietary information, or if you even worse, if you start profiting from it, if you start selling it or start building compatible or competing products based on what you discovered through reverse engineering, I think you're just inviting legal trouble. I wouldn't recommend it. So there are different types of reverse engineering. There are roughly three major groups. You could do completely black box reverse engineering by just analyzing data and communications. So what I mean by that is that you could, for example, analyze proprietary data formats by just taking a data file, let's say a graphics or database storage format, and just looking at the binary files and try to figure out how it's built, what the structure is of that file, without ever looking at the code of the application that produced that file. That's what I mean by that. And another example is to capture a network protocol and look at that and try to kind of figure out how that protocol is put together, what the different fields are, what the different actions are, without ever laying your eyes on either the server or the client that produces that communication in that network protocol. And that is always very difficult to do. It requires careful experimentation and use of binary editors and capture tools like Wireshark. The next big group is when you're doing disassembly. And disassembly is a conversion of compiled binaries to human readable machine instructions. And it could be either native code that's executed on a hardware processor, or something called P code or portable code. This is something that Java applications are compiled into, C#.NET applications are compiled into, what Python applications are compiled into. So it's sort of like intermediary representation of the original program, but not yet the native machine instructions that are executed on hardware. And when they're being executed, there's actually an extra step that converts P code to native instructions. And finally, there is decompilation, and this is where you attempt to recover original code from the compiled binary. So, for example, you take a C compiled binary and try to recreate a C source code. For native code, results for this process are really spotty because there are a lot of code optimizations that go into compilation. There are a lot of things move around, and usually the C-like pseudocode is the best you could hope for natively compiled binaries. But for P code, the results are much, much better, and I'll show some examples of that. There's also static versus dynamic analysis. And static analysis is when you just take an executable, you're not running it, but you're just picking it apart and trying to see how things are put together and what the logic is. And it's very useful when debugging is either not possible, you just don't have the platform to run this application on, or there are all kinds of anti-debugging measures employed, and it's easier to just look at the code. There's also dynamic analysis where you actually execute the application and debug it and look at the code in action. And in those cases, it's easier to do that when the code is obfuscated, compressed, encrypted, and it's kind of reveals its true self through execution. Let's say things are decrypted on the fly. And it usually helps confirm insight that's gleaned from static analysis. And disassemblers and decompilers are often integrated with debuggers, so there's some help there. And usually a combination approach works best. Some things you can reverse statically, some things you can reverse dynamically. So let's look at some examples. So let's say we have a very simple C program that has a password. By the way, don't do the like these are sample applications. They from in terms of security, they're pretty bad. Like things like hard-coded passwords. Do not follow those design patterns, please. Things are done this way just to illustrate a point and to show you how you can actually recover knowledge through examining code that's bad from the standpoint of secure software development. So let's say we have a very simple application that has an embedded password, and if you supply that password on command line and it matches what's hard-coded, it returns true, otherwise returns false. So it's a fairly simple application. And when you compile it, I don't know if you've ever done that, maybe out of curiosity, you open the compiled representation. What you see inside is just a huge pile of junk. There's just nothing that resembles the original program, and most people are at a loss at what to do next. I mean, what am I looking at? And that's quite understandable. It's not humanly possible to analyze that without proper tools. So let's look at what the tools can do for you. So same application, let's open it in a disassembler. So disassembling comes with all debuggers, pretty much, at least those that debug in native machine instructions. And when you open the same application in a disassembler, things all of a sudden look much clearer. You may not know the assembly instructions that are here on the right hand of the screen. However, if you kind of look closely, you could find correspondence between the C statements on the left and the corresponding machine language instructions that were generated from those C instructions on the right. So if you look closely, if you arm yourself with the machine language manual, if you study what different commands are, like the ones that are in the blue here, like move, add, call, test, once you understand what those commands mean, you will be able to slowly figure out what the application does. So as you can see, things are looking much better when you have a proper tool to look at this compiled representation. With decompilers, and remember, disassemblers reverse things back to machine code, but decompilers try to reconstruct the original source code. The compilers, you can actually do even better. This is the result of decompilation of that same program into something that resembles C code. You can see that things are almost like the original. They're the same commands there. The compiler was smart enough to figure out what the different variables are, what the function call is, and so certain things are lost. You can see that certain names are no longer there. Of course, comments are gone. But looking at the decompiled representation, you can see that the things look much better, and it's actually easier to understand what's going on here. I mentioned portable code. With portable code, the compilation is often very very precise, very like almost the exact representation of what the original program was. So in here, you see a Java source code, a simple Java program. When we compile it and then use decompiler to decompile it back into the original Java code, you will see that decompiled representation is almost an exact replica of what the original code was, and you can clearly see what's going on. There are a few quirks here and there. Again, comments are gone, maybe some names are gone, but things are very, very clear. Same thing goes for C# compilation. If you ever open a C# compiled application with a decompiler, you will see that it decompiles very well to the original C# code, and you can see the algorithm very, very clearly. What tools can you use for reverse engineering? Well, IDA Pro is pretty much synonymous with reverse engineering. It's probably the most famous reverse engineering tool. It has tons of support for many processors, environments, has disassembler and debugger, and also a decompiler add-on. It's called Hexrace, has plugins, scripting, all kinds of things. It's super, super powerful, but it's kind of expensive. A single license would cost you from $2,000 to $4,000 US. Ouch. But there are free versions out there. They have limited functionality, but you can actually pick them up, pay nothing, and do reversing on Windows, Linux, and Mac for free, which is not a bad deal. And there's also a home version for professionals for $300 something. So there's also a tool called Hydra. It's open source, so totally free, open sourced by NSA of all organizations. Has many supported architectures, has a disassembler, decompiler, now has a debugger too. Also has plugins, scripting. Oops, sorry. It's kind of rough around the edges, I would say. It's a little less polished than IDA Pro, but it has a lot of power, a lot of functionality, and it's free. So you can't beat that price. And these are two tools that I've highlighted, but there are many, many more. There's the whole radar environment where there's it's a very, very powerful tool. Plus, it has a Cutter graphical user interface and many other interfaces. Binary Ninja is also a very powerful and popular framework. There are standalone decompilers, debuggers. There are things that are built specifically for specific languages, like for .NET compiled executables. There are certain tools. There are other tools for Java, for Python, for WebAssembly. So just lots and lots of tools, and most of them are free. There are even specialized virtual machines that you can download. There is Flare VM for Windows. It's based on Windows. And Remnex, it's a Linux reverse engineering tool bench. And the list just goes on and on. So reverse engineering actually has a lot of obstacles, and I to being successful in it. I think that's what scares many people away. So first of all, as part of compilation and optimization, code is usually made more difficult to reverse. Things move around. Meaningful names of functions and variables are lost in the process of compilation. Comments, of course, are lost. Structure of data is very often lost. Such language constructs as objects are lost, and it's hard to kind of reverse them and put them back together. Variables frequently move between stack and registers, and it's hard to figure out what goes where. Execution flow is obscured, so what used to be a loop turns into this convoluted mesh of various comparisons and jumps in the machine language, and decompilers do not always do a good job recovering those loops. Same goes for conditional statements, exception handling. So all those nice language constructs you're used to, trying to recover them is a challenge. There's also function inlining, where copies of function are copied all over the code, inside the code, and libraries are often embedded into the body of code, and that just makes the application explode. So you have, let's say, a 10-line C program that links in like 10 different libraries, and all of a sudden you have an executable that's 10 megabytes in size, that has millions of machine instructions, and you have to figure out what's your original application that you're looking at, and what were these huge loads of libraries that were linked in, and really are not that interesting to look at. Not only like some obstacles come naturally, but software publishers are not stupid. They understand that they want to, in order to protect their proprietary software development secrets, they want to maybe employ some counter reversing measures, and there are lots of those. Some software publishers try obfuscation, so there are tools that deliberately mangle symbolic names in, let's say, in scripting and portable code languages, so they become like a simple name, like, I don't know, test1 becomes a mess of all kinds of special characters and characters from our other alphabets, just so that your brain will explode when you try to analyze what's going on. Code is frequently minified. Those who are developing for the web, they see this very frequently, where nice JavaScript is compressed into a very tight bundle of minified JavaScript code. This is done for size reasons, to reduce volumes of data that need to be transmitted, but also does a good job of obfuscating the logic. Code is often compressed. There are special tools called packers that exist that compress your executable and maybe encrypt it too. And the way it works is that when the application runs, it loads a part of itself in memory, decompresses it, decrypts it, and then runs it. So if you're just looking at the code statically, you have just a huge mess of compressed and encrypted data, and a little bit of piece of code that opens it up and runs it. So you have to jump through all kinds of hoops to get to the original logic, and there could be multiple nested levels of that. There are all kinds of anti-disassembly disassembly tricks that are used to confuse debuggers and disassembly tools. There are all kinds of jumps and false branches, self-modifying code. There are a lot of anti-decompilation tricks that can also be employed. And that's because decompilation by itself is a difficult process. And when things are compiled intentionally in such a way as to confuse the decompiler, things get ugly very quickly. And also, as you step through the application, there are anti-debugging measures. There are all kinds of insertion of breakpoints, use of debug handlers, signal-based execution. There are all kinds of interesting tricks that software publishers use to slow down reverse engineers. So it's not all an easy process to analyze. And this is by no means an exhaustive list. This is just a taste of what expects you when you try to reverse engineer something. But it's an arms race, really. Good debuggers and virtual machines can hide their presence to a degree. So application that tries to detect if there is a debugger running and do things to obscure behavior, it cannot always detect that there is a debugger running because debuggers are getting smarter. Disassemblers and decompilers are getting smarter to overcome some of those measures. There's also deobfuscation and decompression tools that are available. So just bottom line is expect these challenges in your reverse engineering work. And the bottom line is there's nothing that is not reversible. It's just all a matter of how much time and effort you're willing to spend to look at something. And I guess the hope from software publishers here is that things get so complicated that you give up, that it becomes not worth your time to reverse engineer something. But there's nothing that's impossible to overcome with just adequate techniques and tools. So if you want to actually start practicing, I would suggest several stages for how to do this in a more organized, controlled fashion. And the only way to do it, to do a reverse engineering, to get good at reverse engineering, is to study and practice. You cannot just pick up a book and then by the end of reading it become an expert. It's not how humans learn. So I would say to get started, you need some prerequisites. You could jump in without having any knowledge about anything, but it'll be a very slow process and you'll be stumbling a lot, and you will have to do all kinds of Google searching and proceed very, very slowly if you don't have some basic knowledge of the following topics. You probably have to have at least a beginner ability to write in some programming language. Most languages are fine, but C and C++, because they're so close to how they compile things, so close to actual machine architecture, I would say it's an asset to have either C or C++ knowledge. You probably need to have a basic knowledge of target computer architecture, maybe some common machine language instructions, what the registers are, how's memory organized. It's going to help you. General idea of how compilers operate is useful, because you could probably imagine then how an if statement in C language could be turned into a set of machine language instructions, and what that would look like, or how a loop could be represented in machine language instructions. That'll make things a lot easier for you if you understand that. And of course, you need attention to detail and patience. I mean, I'm sure, as you've seen from examples I've shown, if you're not interested into in digging in and looking at the details and exploring, and if you're impatient, I don't think you'll enjoy it. I don't think it's this activity would be something that you will that would be for you. And of course, you can learn as you go, but having these prerequisites helps. And then I would suggest that you start with do-it-yourself code samples. And the way this works is just write a few very simple programs, like a bubble sort, or a simple application that asks asks a question and waits for an answer and prints something. So write a few little programs like that, and then compile them, and then look with different decompilers, disassemblers, look at compiled representation. And the reason why this is useful is that you know exactly what the end result of your reverse engineering efforts should be. You know what the original program looks like, and this removes that element of the unknown and allows you to concentrate on just looking at how things are compiled, how they're represented in native code, what the different additional code that compiler injects into the executable, because there are all kinds of service code that's being added, like a setup, teardown, function prologue, epilogue. There are all kinds of interesting things that are not part of your original program that are added to the executable anyway. And you can try debugging. And it's just a less intimidating way to enter reverse engineering. Then, once you've mastered that, you're ready to tackle some what they're called crack me's, and these are challenges designed by someone else. And usually, these are small applications that are hiding a secret. That's called a flag. If you're into CTF competitions, you're very familiar with the concept. And this is something, some executables they can download from the internet, and this is the website that my favorite. It's my favorite for that. It's just a great resource. It's a big directory of all kinds of challenge sites where you can just sign on. Look at different sites. Each site has lots and lots of different challenges, and some of them are reverse engineering challenges, so you can concentrate on those. And you just basically go at your own pace and try, start with simple stuff and go to more complex stuff. And it has a global scoreboard, so you can compete with other people. I find that's useful encouragement. Then, as a next level, you can try CTFs. These are online and in-person competitions. You're probably familiar with them, and they come in all levels, from beginner to pro. They occur all over the world. Reverse engineering challenges are very commonly found in CTFs. Almost every CTF I've ever played in had reverse engineering. So it's something that adds an element of time to your learning. And I find that time pressure kind of really puts learning into overdrive, at least for me. And there's a great resource called CTF Time that lists all kinds of CTFs that are planned for the next however many months, and you'll find that pretty much every week there's at least one or more CTFs going on somewhere in the world, and you just can connect online, no pressure. You don't have to win a CTF. You can just compete. It doesn't matter which place you come in, but you get to try interesting challenges and sharpen your skills that way. And and there's also a global scoreboard. And finally, like, once you become a real pro, there is something that I would call an Olympics of reverse engineering. It's created by FireEye, a famous security company. I would say it's the toughest reverse engineering competition in the world. And if you know of something that's even tougher, please let me know, because I'm really interested in that. It's been running for several years now. There'll be a new one hopefully this year. They run, I think, like September through November, or like August through October, like in that time frame. They usually have just 10 to 12 challenges of increasing difficulty, and you have 40 days to reverse them. And that sounds like a lot, but it's not. Trust me, it's horrible in terms of difficulty. Like, the first challenge is very, very easy. Pretty much everyone can solve it, but then difficulty ramps up really, really quickly, and in the end you can spend 1, 2, 3 weeks on a single challenge just to try to figure out what the flag that's hidden inside is. And they're very interesting challenges. A lot of them come from real malware samples from all kinds of platforms, scripting, mobile, embedded, esoteric programming languages, you name it. It's really, really interesting. And because this security company, they base a lot of their challenges on real samples of malware. And an unusual thing for it is, if you finish all the challenges, no matter which place you come in, you get a prize, which is awesome. I'll quickly touch on reverse engineering challenges, because I think we're getting close to the top of the hour. I think to really be successful at reverse engineering, you have to make it an enjoyable experience. Things, like many things in life, things go much easier when you enjoy what you're doing, because it requires a lot of time, patience, attention to detail. Make sure it's something you're motivated to do. Like, you're solving a puzzle, you're trying to find a secret. These are my motivating factors. I think it'll go much easier. You'll enjoy it more if you find it fun. Reverse engineering is tough. It's very easy to get lost in the details. So I think you need to be very concentrated on what you're trying to do. Even an average application like Windows Notepad, when you open it up in disassembler, it's huge. It has like 17,000 machine instructions. It's just unrealistic to. It'll probably take you days and weeks to fully reverse it and understand what different parts are doing. That's not the goal. Usually in reverse engineering, your goal is really focused. You're trying to find the bug. You're trying to discover a hidden flag. So it takes practice to to be really focused and concentrate on finding the specific thing you're looking for, and not be distracted by everything else around it. So try to do that, and then as you go, maybe expand your understanding around that piece of code that you're looking for, and not try to kind of boil the ocean. But as I mentioned before, combining static and dynamic analysis is very useful. Use debugger for analysis. Analyzing by hand is tough. Um, um, Make the debugging tools do the heavy lifting. So to bypass encryption and obfuscation algorithms, for example, what I frequently do is I get the application to do the decompilation, to deobfuscations. Just a matter of cleverly setting up breakpoints, moving control between different parts of the application to get it to do these processes, rather than you doing it by hand. You can bypass problematic code. You can jump around. I mean, there's nothing that says that you have to execute the program exactly as it's written. The world is your oyster. You can do pretty much anything you want in the debugger. And static analysis can be made simpler by scripting some parts of the reversing work. I frequently use Python to decode different parts of the algorithm rather than doing things by hand. So scripting is built into a lot of tools, and it's just it's very, very useful in that regard. Very often, things you're looking for can be found by carefully looking for different what I call them signs. Let's say you're looking for a particular encryption algorithm that's embedded somewhere in the application. Well, there are probably magic numbers around that place somewhere that are frequently used in encryption and hashing algorithms. You could tools can highlight certain interesting algorithms, and that can help you pinpoint the area you're looking for. For example, if you see that you're looking at the big application, and then all of a sudden there is an area of it that uses a common encryption algorithm, that may be a sign that maybe there's something interesting hidden in there. There are all kinds of system calls and library functions that the native code would call that also tell signs that maybe there's something that what you're looking for is hidden there. So that's a good feature to look for. And there are lots of tools and plugins to help. And also, because this is such a data intensive and knowledge intensive activity, documenting things is crucial. Like as you go through the code, it's very important to immediately document in the form of comments, for example, the things that you find. Let's say you discover that some algorithm does sorting. Immediately in the tool, you can rename algorithm that has, when you decompile, has some kind of generic name, function 123, rename it to, let's say sorting function or decryption function. If you find the variable and you figure out what it does, rename it to indicate its purpose. A lot of these tools allow comments to be added as you decompile and analyze things, and then just rinse and repeat. This is how reverse engineering, I think, can be done effectively. Is just little by little, you discover different things, you document them, and then you dig more. And it's an iterative process. There are lots of resources for learning reverse engineering. Google is your helper here. There are conferences geared specifically towards reverse engineering. Interestingly, one of them is in Montreal annually. So that's something to check out if you're interested in this area. And there are lots of discussion groups online. There's reverse engineering Discord. There's Reddit and Stack Exchange groups where you can ask questions. And there are lots of people there that know their stuff and they can answer. Lots of books. Well, not lots of. There's some books on reverse engineering that may help. So to wrap up, a lot of software and hardware around us are black boxes. If you're curious about what's inside, reverse engineering allows you to open them up, understand how they work, and you can help make different products and software more secure, build compatible solutions, and modify them in new ways based on knowledge that you acquire through reverse engineering. There are lots of tools available to help you. And as you learn more about it, I'm sure you'll enjoy reverse engineering as a fun and really intellectually stimulating activity. If you have any questions, I'll be happy to answer. Once again, here are my handles where you can reach out. And I put copy of the slides on my GitHub if you want to look at some of the information presented. Yeah, and with that, I thank you.
Excellent. That's been a perfect introduction, especially for me because I'm not familiar with this field. So definitely today I learned. The links are awesome, and thank you for sharing the presentation. If you can actually cut and paste your GitHub there, I can
Yes.
paste it in the link here, or you can paste it in the chat. And then all the other links are made available because it will be in the YouTube chat. I guess the first question that comes to mind for me, well, I'll let you do that, but
Yes. Yep.
the question that comes to mind in terms specifically in the CTF is the reality of CTF versus what you would find in the wild. Now I know that Uber Olympic CTF is probably the true example, but for learners, it's I guess to me it would be these are great practices, skills, but you may not necessarily see these examples in the wild. Would that be a fair understanding?
CTFs are interesting beast, and there are lots of actually complaints about CTFs being unrealistic. You have all kinds of interesting challenges that do not, many of which do not have immediate application in the real world. So, so I think, um, so I think that's partially true. A lot of problems that you see in CTFs are kind of artificial. Um, the when if you're a part of a blue team, for example, or even if you're part of a red team, if you're a pen tester, the real world problems that you're trying to solve do not often resemble the types of challenges you see in CTFs. But I feel that CTFs are still very useful in terms of um, building your skills. Um, if Garth, I don't know if like I know you're into martial arts, right? So the things that you do when you train in your martial arts class, this is not something that you would see in real life. Like you'll probably not be having a rule like a rules based a fight where people follow certain agreed upon rules. They'll probably be using all kinds of dirty tricks. So your martial arts training is not exactly what you see in real world, yet your martial arts training prepares you for those dangerous situations that you may see in the world out there. Is that would that be a kind of a good analogy, you think?
That's an excellent metaphor. Never bring a knife to a gunfight.
Yeah. So I find that speaking for myself, the challenges that I see specifically reverse engineering challenges I see in CTFs, there most of them are artificial. You will pretty much never see the similar problems if you try to solve a real world reverse engineering problem in the field, but it does build your muscles. Reverse engineering muscles does introduce you to all kinds of interesting techniques, and bits and pieces of those techniques you do sometimes see when let's say you try to reverse malware, because uh, I would say malware authors are very conscious of antivirus companies picking up their code and trying to figure out how it works. So they do for sure all pretty much always employ anti debugging tricks, anti disassembling, anti decompiling tricks, you name it. So that area is actually probably one of the most realistic ones where you'll see things that you will see in CTFs. But just as a practice, CTFs are, even though they may not be fully realistic, they're still a great practice. Garth, I'm missing a comments box. Like, I see the comments posted, but how can I post a comment? Like, I want to post that that URL that you mentioned.
Do you see the comments? So do you see on the right comments, banners, brand?
Yep.
Okay.
I see comments banner.
Top
but there
comment
is
there,
Mhm.
and hit that, and you should see it toggles between display and not display. And when you display it, you should see a list of previous comments as well as essentially what other people have commented in the chat.
Yeah, I see that, but I don't see a box to post my comment in there for some reason.
All right. So if
I'm posting in the internal people chat.
Yep, and
maybe you can relay that to the comment section.
Will do. That's maybe a StreamYard we are not familiar with, so it should appear shortly there. Awesome. Your go-to tool
for reverse engineering, I would say IDA Pro is the most polished one. It's been used for so long and by so many people that most of the bugs have been worked out. So the cost is a concern. So if you work for an employer that can buy a license, that always helps. But I would say, yeah, IDA Pro is probably the best in my experience. Hydra I think is catching up because so many people are crowdsourcing their efforts to add new functionality to it, to fix bugs. I think it's becoming better and better. And I'm sure, like, if somebody who is listening who has other favorite tools, they'll probably be mad at me and say that no, that's crap. There are much better tools out there, but these are the two that I usually use. But this is for decompiling, disassembling native code. For Java, for .NET, there's a slide where I listed some of the tools that I use for those platforms. Unfortunately, not every tool can do everything, and you kind of have to have a tool bag.
Right. Which is pretty much the same for everything in security work. Thank you very much for this excellent introduction. It will be, of course, in our YouTube channel for anybody to watch at their leisure. So thank you again for stepping up and presenting to us. It's always a pleasure to have you in OWASP Ottawa, and hopefully at some point in time in the future, we can actually do it live as opposed to from our COVID bunkers. Hang around after we sign off and we can have a chat. So that's it for this month. Look for all our usual anti-social media for future postings, for future presentations. We are always available on the usual channels that you will see in the public service announcements at the beginning of the talk to communicate with us if you have questions, suggestions, ideas, or you want to present. This is OWASP Ottawa again, signing off, and we will catch you next month.
Thank you.